We now have Dr. John Harvey to speak on the preservation and quality of life with some framework and examples through his presentation. Dr. Harvey, that is professor of civil environmental engineering and chair of the Transportation Technology and Policy Graduate Studies program at UC Davis and director of the UC Pavement Research Center at the University of California, Davis and Berkeley. He is principal investigator for the Caltrans-sponsored partnered Pavement Research Center for research, development, and implementation of a wide range of pavement technology, management, cost, and environmental topics. He is also principal investigator or co-principal investigator on a number of projects for the FHWA and FAA. His BSc is from Oregon State University, and his graduate degrees are from UC Berkeley. He is a professional civil engineer in California. Please help me welcome Dr. Harvey.
So basic idea here is beginning to put together a framework for a road is not just a road we use for motor vehicles, we use for motorized transportation. A road actually has a lot of other roles and has a lot of other impacts in addition to those that previous speakers were talking about. So I'm not really going to talk about environmental sustainability, and I'm not going to talk about optimizing and preserving all those important things from a motor vehicle point of view, but think about some of the other purpose functions of a road and how those also affect human quality of life. So we've talked about safety, things that we already consider in our pavement management systems and life cycle cost analysis. Safety, the ability to access essential services, healthcare, nutrition, education, social access, recreation, cost and comfort of access in motor vehicles. What we're generally not considering are noise, the role and use of the roads for active transportation. And active transportation basically means non-motorized transportation, ride quality, safety, and then roads also can have an impact on thermal comfort in some contexts. There may be other things. We're actually putting together a framework for human quality of life and roads and preservation right now. So most of you know what that is, right? It's not a drive-in movie screen. That's a noise wall in Los Angeles. These cost $1.3 million a mile to build. They cost about $100,000 a year to maintain. And most of that maintenance is another human quality of life. There have been studies that show if you live in a graffiti-filled environment, it actually measurable levels of stress indicators in your bloodstream, having to deal with graffiti, particularly criminally related graffiti. So that's a cost about $100,000 a year. You can't put these everywhere. They limit future transportation, highway expansion for whatever mode of transportation. And personally, I can tell you that the sound wall that's a quarter mile from my house basically protects the people in the shadow of the sound wall and drives all that noise into my bedroom window at 5 o'clock in the morning every summer morning. Thinking in terms of, so I'm going to give you a couple examples of some studies we've been doing on things that affect human quality of life. We did a noise study, tire pavement noise study in California. Started out with asphalt, and we did 6 years of measurements, and then we did 4 years of measurements on concrete pavements in the state. And so this is kind of a quick summary of the results of those. How did we measure noise? We used what's called onboard sound intensity. Onboard sound intensity, we put microphones next to the tire pavement interface and collect that tire pavement noise as we're rolling down the road. We're also correlating that with macro texture and IRI and potentially some other things. So on the back here, we have our profilometer with our high-speed laser picking up our macro texture, and the other one's picking up the road roughness. So I'm not sure how many of you are familiar with what causes tire pavement noise. There's Two main mechanisms. At low, the low frequency noise is primarily caused by the tire rolling over the positive macro texture in our surface, which causes vibration of the sidewalls of the tire. And your tire is actually a drum that's being beaten on the bottom by the positive texture and transmitting that out through the sidewalls of the tire. Air pumping is the other frequency. That's the hissing sound that you hear. And that's basically the tire, as it comes around, is squeezing air out from between the tire and the pavement. And the longer that path that air has to go, the faster it's going to have to move to get out of there, and the higher the decibel level of that hissing noise. So if we can give that air a short path to get out from under the tire, we can drop the high frequency noise. This is on so these are different frequencies on what's called a 1/3 octave band analysis. These are sound intensity levels in terms of adjusted decibels, and the A in that is adjusted for human perception of different frequencies of noise. Humans hear best, so part of the reason that peaks at the 800 to 1200 hertz frequency range is because that's the range where we actually hear the best as humans. That's where human speech is primarily. So we partially peak there because of the weighting, but we also peak there because the size of the tire tread block snapping down and snapping up at 60 miles an hour is at 1,000 hertz. So there's a part of this tire pavement noise that we can't actually control, and it has to do with the aggressiveness of the tire tread in there. But we can affect to the right of that, to the left of that to some degree, and to the right of that to some degree, particularly with our preservation treatments, because we're treating the surface and dealing with texture and porosity of the surface. So this is our asphalt test sections spread across California. The experiment design, we had 54 general sections, 4 mixed types, dense graded asphalt as a control, open graded asphalt, rubberized open graded, which you use quite a bit of in California, and rubberized gap graded. To try and we didn't want to collect data for 15 years, so we compressed things, and we selected initial ages of less than a year, 1 to 4 years, and greater than 4 years, and then we monitored that over 6 years, and that's where we pick up about a time scale of about 15 years over which we can understand tire pavement noise. Different traffic levels, different rainfalls, and we had some what are called, we borrowed some Oregon F mixes in California for a while, which Oregon went to some very big stones in their open graded to try and get them to last longer. John Coplantz isn't here, but the general conclusion is they don't last as long, and you basically can't talk to the person next to you or even yell at them and get them to hear you because of that macro texture in those 19 millimeter, 3/4 inch open gradeds. We did not control for aggregate size, although I'll mention a couple other studies we followed up on that. Because of lack of as-built at the time, which has since been filled by Caltrans, we lumped together polymer and conventional binders. We don't use a lot of polymer in California, primarily rubber instead of conventional. This is a busy graph that shows, this is onboard sound intensity, so this is the noise. These are dense graded mixes, and so this is each year of the campaign. So there's 6 of these for the early life, the ones that were just born when we started this study. These were sort of the toddlers when we got started and following them through, and then these were the ones that were older for 4 years through. But through that, you see a general trend of the dense graded. This is the open graded, which tend to start quite a bit quieter, but tended to get back up towards dense graded noise levels over the course of the study. This is the rack G, which was very quiet, and we didn't understand why at first, and I'll give you the answer in a minute. Got back up over there, and then this is our rubberized open graded, which has that early open graded quietness, but doesn't increase in noise that much. The takeaway, I can't remember if I put the takeaway on the next slide. Okay, I didn't. The takeaway is why is rubberized so quiet at the beginning? Because we didn't have a density-based compaction spec. We had a method spec, and what we found out is our gap-graded rubber was basically open-graded until traffic turned it back into a gap graded and drove the air voids down from 12% to 7% in the first 2 years of traffic. We now have a density spec on this, which we think will make that gap graded. It's a great performer for reflective cracking, make it even better. Main reason that the rubber stayed quiet, open graded, and the conventional and the few polymers in here didn't, is because the rubber didn't ravel, and most of that noise increase in the gap graded is that it ravels somewhat faster than our rubberized, and that's why we believe that the rubberized open graded is staying quieter over the long run. It also didn't reflect the cracks as fast as well. Cracks actually will give you spikes in noise. So this is kind of a cumulative over those 15 years. So the really quiet ones would be those early open gradeds. These are the older ones as they get noisier. And this kind of gives you an overall look at it. Humans can't perceive noise changes over more than about 2 decibels. Federal Highway's noise manual says 3 decibels. We actually kind of did some anecdotal testing, and you can generally pick up about 2 decibels. So if you're less than 2 decibels different, it doesn't really make that much of a difference. If we look at the 50th percentile here, so here's our HMA. That's at about averaging at about 103, and that was our kind of our baseline comparison. Does using these other treatments potentially give us a measurable benefit that's going to last? Here's the rubberized, here's the open graded. So it is quieter early, but if you look across the demographic here, it's not that much quieter. It's about 1.5 dBA quieter. The rubberized gap graded similarly. The one that really gives us at the 50th percentile across this 15 years of compressed data is the rubberized open graded. Now, I've talked to Bouzid Choubain from Florida, for example. They have not had as much success with their rubberized open graded in Florida, so this is somewhat California unique. I don't know what we haven't figured out the difference between that, but this just also basically gives you a framework of how to look at dealing with tire pavement noise through pavement service. This is a summary. We put all this data together, did statistical performance modeling, and I'm using speaking Caltrans here a little bit. That's a very high traffic level. That's a 20-year traffic level of about 60 million easels. This is a million easels over 20 years. Overall, this is in terms of time to get back to the same noise level as that average dense graded mix. And this is, I can look at it here, but I can't point at the same time. So the open graded on given us about 10 years of noise performance. Now the last couple of years of that, it's approaching, whether you can perceive that, but this is a metric we're using. The rubberized gap graded, not as much. It's not actually originally intended. There was a lot of talk early about rubber being an absorbent material and having a high impedance, and we did impedance tests all over the place and stuff, and it's not really absorbing that much noise. It's really about noise generation. Pavements don't absorb that much noise from what we can tell. If you think about it, the tire pavement noise is going that way and the pavement's that way. There's not a lot of stuff coming at the pavement that it can absorb it. The performer, at least with the California mixes, is the rack O, which is giving us up to 15 years of life, and we didn't see a big traffic difference between those. This is in terms of IRI over that same data set. And again, and we're using 160, I can't remember why we picked that and why not 170. I think it was just sort of where the data broke in half. So we picked that as a middle performance. Again, the rack O, the rubberized O, is giving us the best performance across that. You can see that often the rack G is giving us pretty good performance, and it's important to remember that the gap graded rubber is usually half the thickness of the HMA in the same application in California. So that's half thickness of rubber. So getting pretty good performance, both the ride quality and the noise across that. So then we have Danish partners in the Danish Road Institute, and they're very interested in noise. They're a very smooth, if you look at the demographic of their network, they're smooth in terms of IRI and heavy macro texture, very heavy macro texture. California, we have a very rough network if you read the newspaper every year when TTI comes out with their survey. And but we're much lower macro texture because we're mostly dense graded. So we're looking at this and saying, well, if they're rubberized, and those are 1/2 inch, 12.5 millimeter max size, most of those, what if we reduce the macro texture and use 6 millimeter stones and still try and keep an open gradation on that? Can we keep the air pumping reduction and reduce the macro texture reduction? So can we get even better with our open graded thin? And the other idea with these is then if we reduce the stone size, can we reduce the thickness that we need, and therefore not only keep the performance from a functional point of view and a structural protection point of view, but also just use less material to do that. So we brought it down, and we're aiming at about a 6 millimeter, 5 millimeter number 4 maximum size, approximately, shifting that gradation down. We built this on a test track, very much like the demonstration yesterday. When we get really thin with that open graded layer, one chunk of something that isn't, it's a little cold, and you start dragging it. So there are some issues with that super thin paving. But this is on a test track. We weren't long enough that we could actually get up to 60 miles an hour, so we could max out at 35 miles an hour. But here's our traditional 9 millimeter mix, which is already fairly small, 3/8 inch, and you can see that the shift happened. What was interesting, and we haven't completely figured out, is we didn't get the shift so much on the lower frequencies where we expected it, but we got them on the higher frequencies, which is more the air pumping. We haven't completely figured that out, but we definitely got a noise benefit. Now, in terms of durability, we were also surmising that, or assuming that you have far more contact points. Open graded fails at those few contact points between the stones. So we threw these in a Cantabro device in our laboratory study looking at these mixes, and here's our traditional mix. I can't remember the exact reason. I think these are just replicates, and we put them in size order. So this is our current mix, and this is with a polymer modified binder. These are our smaller stone mix with the same polymer modified binder, and this is even with a conventional binder. So we think that these smaller stone mixes will also give us a greater raveling life over the long term. So we haven't found a downside to these yet. The one thing that we're a little concerned is that depending on the friction measurement device, if we use the old Caltrans 342 spinning wheel with glycerin, the friction seems a little low, but then when we put a skid trailer, some other friction measurements on them, we think we might be all right. So we're trying to go to pilots right now and make sure that we keep our friction capability on these. But otherwise, they generally seem to be more durable, quieter. Hopefully we keep the same friction. They have a little less permeability, so you wouldn't want to use these. You won't capture all the rainfall for hydroplaning as the thicker mix might have, or a really fast rainstorm. But for most of our rainstorms in California and the West Coast are pretty slow. Not a lot of thunderstorms. So then we said, okay, somebody comes with a new mix. Do we have to build it in order to know how noisy it is? So we had a graduate student do a master's degree on trying to predict noise performance as a part of open graded mix design. We have a whole open graded mix design system that we've worked on, that we're moving towards pilot based on the NCAT system with a few other tricks in it. But we're thinking that we want to look to see if we want this as a noise mix, can we predict it in the laboratory? So basically what we're doing is we're focusing on those two mechanisms in the laboratory. One is that we know that MPD is highly correlated with the low frequency. So we're looking at what's a way to measure MPD in the laboratory on an open graded mix. If you can do that, we can go after the low frequency noise. And this is a device, we actually went back to work by Larry Santucci from Chevron in the 1960s, and looking at quality control using air permeability instead of before nuclear density gauges. And so we've got an air permeability device here, and we're measuring air permeability, and that basically, if we can increase the air permeability, we've decreased that high frequency noise. So air permeability and MPD in the laboratory, we think we can get begin to get an idea of designing this in the laboratory and checking them. So summarizing our asphalt data, at least for the mixes we're using in California, we're recommending rubberized open graded for noise, for smoothness, and for permeability performance. We've got a method, first cut method of estimating field noise in the laboratory, and we've developed new quieter mixes based on these results that we're trying to move towards pilot projects. And if there's anybody from a state agency who's interested in looking at a pilot with some of these on something, we'd be very interested in this. Haven't quite convinced Caltrans to buy an NCAT section for this yet, but that was one thing we were aiming for as well. Okay, concrete test sections. Concrete can be quiet too. Quieter, not quiet. We always say quieter pavements, not quiet pavements. Pavements are still noisy. So this is some work from National Concrete Pavement Technology Center, our colleague Otto Rasmussen, and he looked at diamond grinding, burlap drag, longitudinal tining, and transverse tining. Lots of states use transverse tining. As Larry Schofield was talking about, California switched to longitudinal tining in the 1960s, and we think we're getting as good or better skid resistance with the longitudinal tining than the transverse tining. And Larry can explain in great detail the reasons for that. So now these are the results of, now you won't see transverse tining because we don't do it. These are the results of our California section. So these are these are the number of observations over 4 years of testing. And in general, longitudinal tining is our control because this is what we mostly do. And we do see a little bit of about a one or a little bit more than a 1 dBA on average with our diamond grinding and our diamond grooving. So it will quiet it down a little bit. The exciting thing for noise is looking at grind and groove, which came out of a Purdue wheel track study, and then Larry picked it up, and then Caltrans has built a number of test sections. So I'll show you the results from, it's about 6, 7, 8 test sections that we're now monitoring for noise, the grind and groove. So as we're doing this, we're actually doing onboard sound intensity on the original pavement. So we call that pre-conventional diamond grind. CDG is conventional diamond grind. After the conventional diamond grind, which is what we would normally do, what kind of a benefit do we get? And then G&G is our non-proprietary name for new generation. We call it grind and groove. They had to write a we had to have a Caltransian vocabulary for that again. These sections, these pilot sections that we had, these are the truck lane, which is typically noisier for obvious reasons, more deterioration, and the traffic lane. So each of these is truck lane, traffic lane, traffic lane, and so on. So going from pre-CDG to conventional diamond grind, we're dropping a couple dB there, which is perceptible. But then when we go to the grind and groove, we're dropping a couple more dB. So we're getting down into open graded asphalt starting down here in the 97, 98, 99, 100 range. With grind and groove, we're getting down close to that range of the open graded asphalt. Now, the other thing that I was really impressed by is this is our IRI change. So, and these are inches per mile. So these guys were starting. They weren't that rough when they started these sections up in the 140, 160, 120 to 160 range. Conventional diamond grind gives us most of that drop in IRI. But these are the smoothest pavements that we've measured of any type in California, getting down. I think we have one that's at 38 inches per mile. And with concrete, that means that that inches per mile is going to stay there for a while if we have dowels. That's a whole nother story for another day. Okay, so that's kind of our noise story in a quick nutshell. The other thing we've been looking at is Heat Island, and this is sponsored by our California Air Resources Board as well as Caltrans. This is in response to legislation. I don't think there's any spies here from the California legislature, permission to speak freely. Our legislators kind of read stuff in newspapers and magazines and on the web, probably on YouTube more than anything, and they write laws about it. And so we try and get our science out in front of that policy, but sometimes the policy gets away from us and gets out in front of that. So this is a report that's in final revision and should be out within a month or two. Basically, the idea is total urban heat island. Most of our cities are using slurries and asphalt concrete as their two strategies. And the idea is, what if we make those more reflective, either going to concrete or going to reflective coatings on asphalt? Long story short, we did a life cycle assessment, as I mentioned to Professor Dr. Adams. Life cycle assessment is an approach we use to measure environmental impacts that considers the entire life cycle of the pavement. So we applied this approach of looking at urban heat island. Does increasing the urban heat through darker surfaces increase the electricity use? And if it does, what does that do to air pollution? And for California, what does that do to greenhouse gases? And the presumption from work from one of the national laboratories, where they only really looked at the use phase, was that this was a really big deal because you reduce electricity use. What we found was that the impacts of, if you use that much concrete, not thick concrete, but 4 inches of concrete everywhere, switching the network over to that, the materials production effect on greenhouse gas was between 10 and 1,000 times greater than any savings from air conditioning use. Now, part of that is because we have a very high percentage of renewables in our electricity. Our electricity is very clean, so if you change the electricity, it doesn't matter that much because our electricity is very clean. But the other thing is basically that the materials has a huge impact, and we have to think of that full life cycle. So basically, the idea here was the total urban heat island is not the thing that we should really focus on. What we're looking at now, and I think this is much more important, and there's places where the local street is where the kids play. If you want to walk to school, if you want to ride your bike, if you want to sit in the lawn chair and drink beer in your front yard, you are affected, not anybody here does that, but you are affected by local heat island effects. If you want to, having personally had to change a tire on my car in the Costco parking lot in Woodland, California, when the air temperature was 115 and the pavement temperature was 140, there's some human thermal comfort issues associated with this. So this is what we're kind of focusing on now, is thinking about in those now this has nothing to do with freeways. This is thinking more residential streets and places where there are activities other than just motor vehicles traveling on it. What about human thermal comfort? And this is where we really, it's not just the temperature of the pavement, it's the reflectivity of the light off of the pavement. It's the evapotranspiration. Is that a porous pavement or is that a non-porous pavement? And even just of shading the pavement. So this is the object of some research that we're doing right now. I'm not going to give you any real results on this, but just an idea. This is what we call our Pavement Garden at our research site in Davis. So this is one of the sections. This is measuring temperature above the pavement. And then we have a wall here. So we're also looking at, so you reflect the light off of the pavement doesn't get so hot, but where does all that energy go back into space, or does it hit other things? And so here we've got a concrete surface, pretty reflective. This has an albedo of about 0.3, and that's about 115 degrees Fahrenheit. This asphalt pavement right next to it that's at 140 degrees. So part of this is figuring out, well, what about the pavement itself? And that affects you up to about here, the heat that's actually radiating off of the pavement. But you're also getting hit with the light. If you make it more reflective to cool down the pavement, you'll notice that the wall temperature here is 6 degrees different from the wall temperature there, 6 degrees Fahrenheit. So you really have to model this whole thing. So what we're working on is some models of human thermal comfort, considering reflected light, conduction, direct solar radiation, and how humans absorb this and how it affects your body. So not important everywhere, but there are contexts in which this might be one of those other functionalities that we think about in terms of our preservation treatment. Some are in a neighborhood like this, around the United Center in Chicago. The other thing we're working on this is permeable pavement, which I didn't have time to talk about, but potentially making that pavement fully permeable and evaporating water out of it, your irrigation water or your summertime rainfall, is another potential local cooling effect. So last thing I mention is pavement surfaces and bicycle rider comfort. Economically, there are regions in California where bicycle riders are extremely important, particularly in some of the wine growing regions. People come and ride their bikes and drink wine. I don't remember which order. Actually, it's kind of an alternating thing. And we have massive rides in some of these areas, like along the coast. So this is this drives all the motel business, all the restaurant business, all the tourism business, and so on. And then we're also trying to think, if we've got all these local roads in the urban areas and we're trying to encourage more active transportation, is that pavement serving the active transportation people as well as, not canceling out, but as well as the motor vehicle folks? So what we did is the goal was to develop guidelines for the design of preservation treatments, where that preservation treatment is going to be put on a route that's not only a state highway and a local street for motor vehicles, but those state highway and local roads are being used for bicycles. So we did texture measurements. We instrumented a bicycle to connect mechanistic empirically. Does the vibration match the texture? And does that match the surveys that we did, where we brought in 160 riders? Well, we worked in 6 cities and had 160 riders ride their bike and rate up to 15 sections in each city. So we gave them a route. We measured the texture. We had them ride. We had people at the end of each section and say, rate my pavement. And then brought that into a statistical model. So this just gives you an idea. One of our microsurfacings on one of our sections is at about an MPD of about 1.1. Dense grade is usually at about 0.6. Everybody in these bicycle riders wants hot mix asphalt because it's got an MPD of about 0.6. And our discussion with them is, what are you going to give up? Because that costs 3-4 times more than using a chip. We need chips. We need preservation treatments. This was what caused all the trouble. Is an industry Caltrans group changed the gradations in our 3/8 inch chip so that it had 3/4 inch chips in something named 3/8 inch chip. And they put this down on our most important bicycle route in front of Hearst Castle, where there was this large group of affluent retired doctors who ride their bike up and down that. And those folks, if you Google chip seal disaster, you'll come up with their worldwide petition. And they had these people were connected enough that they talked to the governor, the director of transportation, etc. So this is what kind of triggered this whole thing. So what did we come up with? We've come up with a flow chart that guides a preservation designer, as a treatment selector, through a process of selecting one of the Caltrans standard chip seals and giving them an idea how happy are your bicycle riders going to be. And it's not 0-1. You can have them really happy, a little happy, really unhappy. 80%, bottom line, 80% of the riders rate pavements with an MPD of 1.8 or less as acceptable. So basically what we're doing is limiting the chip seal size. We're able to use our chip seal. That found out we can use our chips. We just have to be careful with the maximum size. All of our slurries passed. They're not quite as happy as HMA, but the slurries were rated acceptable. Distresses, bicycle riders care about IRI, not nearly as strong as macro texture, but there was definitely a correlation with IRI. So keeping those urban pavements preserved, keeping the cracks from getting too bad so they start affecting the IRI, you're not only going to keep the motorists happy and the agency happy, you're going to keep the bicycle riders happy. So the spec recommendations will be in the report. This can be considered in our pavement management decision making in terms of treatment selection, depending on if it's a bicycle route. And then I'm going to point to the presentation by Mr. Gibson earlier today about doing your complete street stuff as part of your preservation program. Cost and public acceptability helping me with that. So how to consider these preservation criteria? The first thing we have to do if we're going to consider these additional functionalities is we need to collect the data and build these models so that we can bring these into decision making. We're trying to fill these gaps. There's really not a lot of information out there about these other potential priorities. Once we have good data, we can do data-driven policy making, bring it into policy, consider it in our pavement management system prioritization and treatment identification, bring this into our standard project design checklist, particularly for local government, but for our lower volume bicycle safe state routes. The key thing is that if we're going to consider this, we first have to build that knowledge and database. Everything I talked about here is in a document that came out in July 2015 called Towards Sustainable Pavements Reference Document. Originally, they were supposed to call it Sustainable Pavements, and we said, prove to me that sustainable pavements is not an oxymoron. Let's look at sustainability as an aspirational goal. So this is basically covers pretty much everything that that we could think of, and a fairly large group of authors that can influence pavement sustainability. And one of the biggest things that we talk about in there is pavement preservation. For affecting sustainability in a lot of the ways that the previous speakers also talked about. So I'd like to acknowledge the sponsors for this, but note that everything that's an opinion here is my opinion and not theirs, and my contract says I have to say that. And also like to acknowledge all the colleagues at UCPRC, Lawrence Berkeley National Laboratory, University of Southern California, Oregon State, and Caltrans, and our 160 volunteers. Thank you.
Thank you, Dr. Harvey. I have to say the the noise work you're doing is something that resonates well. I live in Vermont.
No pun intended.
I mean, I hate seeing, hate's a strong word, of course, but seeing sound walls go up these days, it's just, I know they're coming. They're just down the pike, so to speak, in New Hampshire. They're creeping up north. Yeah. And if we can do anything about that, that's a major success.
I do have to mention a caveat or a disclaimer. Federal policy, noise policy right now does not allow you to consider preservation treatments as a mitigation treatment for pavement noise. If you have the problem, federal policy requires sound walls. Lots of discussion between Arizona DOT and Federal Highways and California DOT and Federal Highways. And basically the Federal Highway Administration take on that is that you can't guarantee me that preservation treatment will be replaced in a timely manner and that it won't go back to the noise because you didn't fund the preservation. So that's a policy issue, just to make you all aware of that. But what Caltrans said is, even if we still have to build a sound wall, we can still make it much quieter, and by using that and also for the occupants of the motor vehicle, it's much quieter as well, so motorist comfort as well.
Mm-hmm. Is that something FP2 could tackle as a policy?
Boy, that one makes my hair for a little while. John, I'm a long-distance cyclist myself, and when
Okay.
you talked about that survey, it piqued my interest. The question is, did you, when you collected the information from these people, did you distinguish between the different types of bicycle?
Oh, heck yeah.
That is extremely critical
Yeah.
because a long-distance bike with tires with 120 pounds per square inch in them and a small seat,
Right.
you can feel every hairline crack in that road. I can tell you from experience.
Right. Well,
So-
what Scott and I are actually bike riding buddies. You know the reason for a seat on one of those bicycles? It's just to prevent the stick from. Yeah. Yeah. So what we did, the initial study, and this is the route I threw it in here. This is the Pacific Coast Highway, and Hearst Castle is right over here. So this is the actual chip that was put down that caused the big wahala. But the initial study was long distance. The what do you call it? No, not the mammals. Sorry, the people wearing not spandex. What do you call the stretchy material? Yeah, the padded pants and the lycra wearing set. There you go, middle-aged men in lycra. So we started with them, and so the initial phase 1 study, and that report's actually on our website already, was the high-pressure tires, etc. And we used 3 frame types. We actually can tell you whether carbon, aluminum, or steel dampens that out better in terms of the vibration. What we then wanted to do to bring that off of the rural roads where the long-distance riders go and bring that into an urban, more commuters, kids, folk getting to work, etc., recreational rider in the city, is we actually handed out flyers and paid people $40 to participate and attracted a much more diverse in terms of gender, age, race, income level. You know, not everybody can afford those bicycles. And the starting point for the survey is we documented the bicycle type and we measured their tire pressure. And so, yeah, now the models we have separate models for hybrids, the long distance bikes, and the commuter bikes. So it's in there. That was a long answer to a short question.
Any other questions?
The process for the rubber, you were saying it was different? You were saying the process, no, the sound levels in Florida relating to California.
Not sound. What Bouzid is looking at is durability.
The durability?
And he said, when I've talked to him about this, that he's not getting as much of a difference between the rubberized, and they use a lot of polymers. So Florida's going more with polymer modified, open graded, and I think to some degree conventional. They haven't seen as big a difference as we had between our rubberized and our non-rubberized in terms of durability, raveling performance.
Okay.
Is that it? Well, thank you, John.
All right, thank you.
Thanks, everyone, for